All right, folks, welcome to lecture 3, where now we're going to go ahead and kind of talk a little bit how we're going to be getting a move on. There's going to be a lot of math here, guys. When in doubt, go through it multiple times. Make sure you're exposing yourself to it and practicing it. It's the easiest way to get better at any of this. So, first and foremost, one of those basic Newtonian rules, force equals our mass times acceleration. So, the force is going to be, obviously, how much we're producing is always going to be equal to the mass of the object in how much acceleration it's had. And remember, that's the change in velocity. Now, we can then go ahead and factor this in that our acceleration is always going to be equal to our force divided by our mass. So, for example, why we care about this is it turns out if we want to be able to accelerate an object faster, so we're talking about an athlete, we want them to literally have a more explosive start. You're going to need to either A, increase the amount of force you can produce, or B, decrease the mass you have, or possibly both at the same time. Now, this is where as a coach, you got to figure out which can you do. If you have someone that's really, really overweight, and let's say you've got a 300-pound individual that's trying to be a soccer player, they're probably a little too big for the sport, so we're going to decrease the mass, and if we keep their force the same, they're going to become more explosive. They're going to have a greater acceleration. Or we've got an athlete that they're at a good body weight for themselves. And, well, we don't want to have them lose weight because that could make them less durable or a lot of other negative outcomes we don't want. So we're going to focus on increasing that force production. And that's why we use things like resistance training. We then have momentum. Notice it's capital M momentum equals our mass times our velocity. It's a quantity of motion. So a shopping cart pushing across the floor or across a parking lot doesn't have a lot of momentum, whereas a car going the same speed has a lot more momentum because it has so much more mass. So what we have here is an example of where physics is brutal. So if you are a 150-pound running back and you need to keep or essentially stop a lineman coming for your quarterback, you have to literally create twice the velocity that lineman is creating in order to have the equivalent amount of momentum and be able to stop them, which is brutal. Now, we also have impulse, which is our change in momentum over time. So this is why when you see people, like if you ever watched individuals doing parkour, you see them kind of doing that land where they bend the legs and then immediately go into a forward roll and get up. What they're doing is increasing the period of time that they are absorbing all of that force. Now, if they were to land straight-legged, they would have a greater amount of force they'd absorb in a shorter period of time. So the impulse would be the same. The key is by increasing the period of time we're absorbing force, it's going to make things a lot more comfortable. So you can look at examples of this when people are breaking boards or concrete. It turns out we're going to have a huge change in force in a short period of time. Whereas instead, you could just press down into the wood relatively comfortable, or you could karate chop, say, a giant pillow, and it turns out you create the same amount of impulse, but you have a much greater period of time, which your hand is probably going to like. So another example of why we're going to use this is when we're going to have really long throwing motions, like someone's going from the windup, so they have a greater period of time to fully produce that force to throw that object as fast as possible. So here are some graphical examples of looking at someone who's doing a long overstretched wind up into a high jump, and then also where they're really leaning back, so they're going to have a greater period of time to produce that force. You're going to be able to create a bigger impulse whenever you're trying to throw an object, or in this example, yeeting yourself over a board or high jump thing. I think I used that verb correctly. If I didn't, please leave a comment. I'm getting old. So it turns out when we're trying to accelerate ourselves, once again, it's that change in force over change in time. We can produce a great period of force, or a great amount of force in a shorter period of time. We don't have to be on the ground as long, and we're going to be able to accelerate even faster. And that's why you're going to see when people get up to super high speeds, their feet barely have a lot of time where they're in contact with the ground. And on the opposite, if we're trying to land and absorb that force, that's a good thing because we're not going to have as high of a peak force we're going to have to absorb. Now, the other thing we can do when it comes to absorbing force is dealing with what's known as pressure. pressure equals the force equals mass times acceleration, divided by the area. So, for example, if you were to go ahead and just, tap your hand on a table, that's going to be fine. But if you had a thumbtack and you tapped your hand down on the same way, that would hurt a lot more, because in reality, you're still producing the same amount of force. However, the area is much smaller, and because of that, you're probably going to have a tack sticking out of your hand. So that's the reason why whenever we're working with athletes, you do want to learn how to absorb force, how to use the entirety of your foot, your hand, your body to absorb whatever forces you're encountering, so you're going to be less likely to be injured. Now, we have what's known as work. Work is going to be simply the amount of force we applied over that distance. So in order to do any types of training, we're going to be doing a certain amount of work. And that's really one of the big underpinnings of getting someone in shape, is having them have the ability to perform work. Now, work is fine, but what we really care about with athletes is going to be what's known as power. Power is going to be our ability to produce that work over time. So for example, if you were to pick up your phone and then you go ahead and you walk all the way across your house and then set your phone down on the other side of the house, that is the same amount of work as if you picked up your phone and just threw it across your house to the other side of it. The key is one of them happened in a much shorter period of time, and that's going to be what is more powerful. So when you're working with athletes, it turns out power in just general absolute is going to be really important for things like offensive linemen, and then power relative to the size of the athlete is going to be really important for things like 100-meter sprinters and even people like long distance runners. Whichever athlete finishes first in a 5K, marathon, etc., that's the athlete that was able to, on average, produce the greatest amount of power relative to their body weight, which allowed them to finish in a shorter period of time. Now, we have energy. One of the first form of energy we're going to talk about is what's known as kinetic energy. Kinetic energy is going to be equal to half of the mass of the object multiplied by its velocity squared. So we're going to have a certain amount of kinetic energy when we're moving. The next type of energy that we're going to have is potential energy. Potential energy is going to be equal to the mass of the object multiplied by the gravity it's experiencing and the height it currently is. So if we have a ball and we're standing on top of a building and we go ahead and we are holding the ball right there, right then the ball only has potential energy. When I let go of the ball's going to start losing potential energy because it's falling, but because it's gaining speed, it's gaining kinetic energy until it hits the ground. And right when it hits the ground, it's going to have the highest amount of kinetic energy, but no potential energy because it's already at the lowest point. And we typically see this in sports. So when you throw a ball, it has both kinetic energy from that velocity, but then potential energy from how far it happens to be off of the ground. So, great example of physics being a harsh mistress of how when you happen to be going at different velocities and different masses, individuals that are much larger don't have to be going as fast to stop individuals that are much smaller. Now, the final form of energy that we're not going to get into frequently in class is what's known as strain energy. Think of like a tennis ball hitting a racket where it's going to be pulling back on those strains. And strain energy is going to be equal to half of the volume multiplied by the stress and the strain. Or we can see this as half the volume multiplied by Young's modulus, which is going to be a fixed value, and multiplied by the strain the object is occurring. So think about a trampoline. If you're on a trampoline, you're going to have kinetic energy, because that's going to be you physically moving through speed. You're going to have changes in potential energy because you're going up and down. But then the springs on the trampoline, those are going to develop strain energy because they're being pulled out, and then they're going to snap back, converting that back into kinetic energy and sending it in the air. Think about this from a theoretical standpoint. We will attribute numbers to these, but they're going to be much easier to approach. So, what examples can you think of? Well, there's a number of them in the slides. But also think about something else that you might see as far as changes. Now, another component is what's known as rebound. or we're going to refer to it as the coefficient of restitution. Now, this is if we go ahead and we drop a ball, how high is that ball going to bounce up off the ground after its first bounce? How high will that second bounce be? How high will that third bounce be? So if we were to drop a ball of clay, it's typically going to hit and not bounce at all. And that means it has a coefficient of restitution of 0. Now, if we drop a ball and it comes right back up to where it started the first time, which is impossible, but we get pretty close with certain things, that is going to be a coefficient of restitution of 1. And it's never happened that I've ever seen in science because it just kind of breaks a couple rules. There's no such thing as a coefficient of restitution above 1, meaning you drop the ball and then after the first bounce it goes even higher than it did on the first, than where you dropped it from. Now, there's a difference between dropping it and you threw it in the ground. Keep that in mind. But coefficient of restitution is just how high is it going to bounce each time. So if you just drop a basketball, you'll see that first bounce, second bounce, third, fourth, fifth. And if you were actually to graph it and actually measure where the peak of each of those heights were, you'd be able to actually figure out what was the coefficient of restitution of the basketball on each bounce whenever you did drop it. So we're also going to see this to a lesser extent whenever we're looking at things like individual hitting golf balls, tennis balls, or squash ball, where it's going to change depending on the heat of the ball and also the way that you happen to have hit it and how hard. Because we're going to have a little bit of deformation of any object whenever you hit it hard enough. What I thought about heat. Now, all of these components are going to go ahead and influence it. Any of you guys have ever played ping pong before? You're pretty familiar with how spin and friction are going to influence an object and how it's going to take a different type of hop. If you've ever played baseball or softball on artificial turf as opposed to on grass, as opposed to on dirt, all of that is going to give differences in how the ball is going to be played and how you're going to be able to field it when it comes towards you. Now, spin, when it goes and the object actually hits the surface, that little bit of friction is going to cause it to hook in whichever direction it happened to be spinning whenever it hits the ground. And with that, let's talk about friction. Friction is going to be equal to the coefficient of friction, so how much friction there is between the two surfaces, and the normal perpendicular force. Now, the normal perpendicular force is the amount of force going directly into the ground. So it's the vertical force. So if we happen to be on a flat surface, the normal force is going to be going straight down, and we don't have to worry about any of that trigonometry. Whereas if we're doing it on an inclined plane, we have the force going straight in. So we're actually only interested in the perpendicular force going into the surface, whereas the other part of the force is going to have it going to the side. Now, why we care about this is we're going to see that as I put an object on top of my phone, now as I tilt, I'm decreasing the amount of perpendicular force going into the phone. So that's going to be the friction between the rubber backing and then the paper of the back of the Post-it note. And I'm going to be increasing the vector pulling it down the slope until eventually I'm going to get this to the point where it's going to slide off, because the friction pulling it down was great, or sorry, the force pulling it down the slope was greater than the force pulling it into the surface along with that coefficient of friction. So higher coefficient of friction, the better traction we're going to effectively get on that surface. The lower coefficient of friction, the more sliding we're going to have. So a great example of super high friction would be something like we happen to be on having metal on concrete. That's going to be pretty gnarly. Whereas I'm sure all of you guys at one point in your life have nearly slipped or have slipped and fallen on ice because it massively decreases the coefficient of friction. And this is important because it's going to influence how hard you can cut as an athlete. Because think about that phone again, when you're pushing off from a really steep angle, you've got less force going into the surface and more trying to push it backwards. So if you can't get enough traction, your foot's going to slip and you're going to eat it. Whereas if you can get great traction, you're going to be able to cut harder, change direction harder, and accelerate harder. So, example of how that normal perpendicular force is going to increase when we keep adding loads to a sled. Along with, there's going to be influences when we're moving objects. So if I'm going to push my desk away from me, I'm going to be actually making the desk heavier and increasing the friction I have to deal with because I'm pushing in a downward motion. Now, if I was to pick up and pull the desk backwards, I'm making the desk lighter, so it actually is going to have a smaller amount of friction I have to overcome in order to move it. Now, with that being said, we've got three different types of friction. We've got static friction, which is going to be objects at rest. We have sliding or kinetic friction, so once things are moving across one another, and then finally rolling friction. And we're going to find that our static friction is typically going to be the highest value. So you have to keep pushing and pushing and pushing until you can finally overcome and get the object moving. Now, once the object's moving, it's typically easier to keep it moving. And some of you guys have probably figured out this before when you had to move like a really heavy bookshelf or something, but you only had to move it a little smidge. So when you finally applied enough force to get it moving, you moved it further than you were supposed to because you were no longer overcoming static friction. Now you're overcoming dynamic friction. So if we're going to graph it and look at that force production, once we finally eclipse that static friction coefficient with the coefficient of friction and the normal force, we're going to get the object moving, which then is going to switch us over to dynamic friction, which is going to be a lower number that we're going to be overcoming. Now, if we're producing the more force we're applying above that dynamic coefficient of friction and the normal force, the faster we're going to be able to get that moving and keep it moving. And then at the same time, when we're looking at rotational friction, now we're looking at the object itself and how that's going to move. Specifically, what's the coefficient of friction between the object, the diameter of the wheel, and then that normal perpendicular force. So if we have those wheels that happen to be larger, we're going to have a greater amount of rolling friction. If we have smaller tires, we're going to have less rolling coefficient of friction. And it's also important when we're dealing with things like having to drive on icy roads. What can we do in order to help enhance our traction so we're going to be less likely to lose control of our vehicle and potentially risk getting in an accident? Science. So, thanks for listening. I know we're going through this information quickly. Please shoot me emails, give me questions that you guys would like me to field, and we'll keep working through this. Rewatch segments if they don't make sense. And stay safe out there, guys. Thanks for listening. Have a great day.